Hello and welcome back to Miles Maths. Today we're going to be talking about function notation, and this is an introductory lesson even. So, as always with my lessons, you should take notes in your exercise book to make sure that you've got a written record of what we've done and you've understood what we're doing. Function notation is just an alternative method of writing algebra. So if we take an example, we might say that y equals 2x plus 1. We then might want to know what particular value of y is for a particular value of x. So if we were doing this properly, we would say, so if x equals 7, then y would be equal to 2 times 7 plus 1, which is clearly 2 times 7 is 14, so 1 is 15. If you were doing a whole lot of these, this would get very cumbersome. So an alternative method of writing it is function notation. And when we write this in function notation, what we see is that we have function of x, and this just means something that happens to x is equal to 2x plus 1. So what happens to x? X is doubled and 1 is added. That's all f of x means. Notice how I said that. It's written f brackets x close brackets. However, we say this as f of x. And I can use any letter for this. The usual letters are F, G and H. However, in theory, I can use any letter I like. So I could have F of X, I might have G of X or H of X. But G of X and H of X are just something that happens to X. If I now wanted, for example, F of 7, well, F of 7 is just 2 times 7 plus 1. Which, as we know, is 15. However, you can see that this method avoids all this awkward if x equals malarkey, and it shortens everything down, makes everything much more compact and easy to read and quick to do. So, we might try f of minus 3. Could you stop the video now and go and work out f of minus 3 for me? Excellent. I hope you're back and have done that. So this should say 2 times minus 3 plus 1. Well, 2 times minus 3 is minus 6, plus 1 would give me minus 5. So we should have the answer minus 5. And these are some very simple examples. So function notation is just essentially a very compact way of writing algebra and takes up less room and less writing than regular notation. So if we have a look at a slightly more difficult example, then we might have something like g of x is equal to 2x squared minus 4. So we might say, well, what's g of 5? Stop the tape now and go and work out g of 5 for me. Excellent, you should have done that. And we should have written down 2 times 5 squared minus 4. And 5 squared is 25. Double that, I get 50. Take away 4. I should have the answer 46. And you can see that takes up just a little bit less space. If you were doing a lot of these, this would be a much more compact way of doing it. I can also have some slightly strange functions. I can have all sorts of functions. So I might have h of x is equal to 5 minus x all over x, and I might want to know what h of 4 is. So stop the tape, go and have a look and see if you can find out what h of 4 is. Good. So what you should have is 5 minus 4, because all I'm doing is wherever there's an x, I'm putting a 4 over 4. And this is 5 minus 4 is 1. 1 divided by 4 is a quarter. So I should have a quarter or 0.25 if you prefer. Excellent. So at this point, let's look at some kind of reverse problems. We can, so where are we up to? That's EG2, that's EG3. Let's have a look up here at EG4. EG4. We might have that f of x is equal to 4x minus 2. However, we might also know that f of a, some number that we don't know, is actually equal to 26. Well, if I combine these two pieces of information, I can see that f of a would be 4a minus 2. So I know that 4a minus 2 is f of a. However, I also know that f of a is also equal to 26. Hence, adding 2 to both sides, I can see that 4a is actually equal to 28, and therefore dividing by 4, a must be equal to 7. So I can solve basic equations in function notation much as I would in normal notation. I can also try some trickier versions of this. So let's have a look at a trickier version of this. Let's assume that g of x is equal to 3x minus 4. And let's assume that h of x is equal to 6 minus x. We might also know that 2h of x, 2h of x is equal to g of x. So I know that 2 lots of h of x is equal to g of x. Fantastic. So I can start this off by saying 2 lots of 6 minus x has got to be equal to g of x, because 2 lots of h of x, 2 lots of 6 minus x is equal to g of x, and g of x we know is 3x minus 4. So expanding the brackets, I can see that 12 minus 2x must be equal just to 3x minus 4. Add a 2x to both sides. Add a 4 to both sides. And we can see that 16 must be equal to 5x. So dividing by 5, x would have to be equal to 3 and 1/5, or 3.2 if you prefer. So I can solve some much more sort of complex looking problems with this. So one for you to try with EG6. Let's assume that f of x is equal to 2x plus 3. And let's assume that h of x is equal to 3x plus 7. Let's assume we also know that 2f of x is equal to h of x. Fantastic. Can you set this up and go and find for what value of x this is true? Good, I hope you've done that. So, 2 lots of 2x plus 3, 2 lots of f of x, are equal to h of x, which is 3x plus 7. 2 lots of 2x gives me 4x, 2 lots of 3 gives me 6. That's still equal to 3x plus 7, taking 6 off both sides, I would find that 4x is equal to 3x plus 1, and taking 3x off both sides, I would find that x was actually equal to 1. And that ends the first lesson on function notation. Well done. Thank you, and I hope you come back to Miles Maths very soon.